Herkese merhaba. Bugün doçent doktor Ulaş Yaman'ı davet ediyoruz. Buradaki yazılanı herkes okuyabilir ama ben biraz daha kişisel bilgi vermek istedim. Çok doğal gelmedi böyle bir şey anlatmak. 2002 yılında, 2003 yılında onu da unuttuk artık, yaşlandık. Ulaş Hoca ile birlikte biz makine mühendisliğinde lisans hayatımıza başladık. Eko yapıyor. Ses yapması. Okey, Eko yapıyor. Ulaş Hoca'nın soyadı Y, benim de A olunca ilk sene aslında hiç görüşemedik. Ondan sonra mekatronik yan dal adı verilen ama aslında yan dal programı olmanın ötesinde Fellowship of the mekatronik tarzında hani bir zorlu hayat şartlarında beraberlik yaşadığımız ki Buğra Hocam da çok iyi anlatır. Ki o zamanlar şu ankine göre çok daha zordu. Başladık. Birlikte birçok proje yaptık. Laboratuvarlarda sabahladık. Güzel işler yaptık işte. Gerçekten zordu ama çok eğlenceli bir eğitim ve öğretim hayatımız oldu. Ondan sonra ikimiz de yüksek lisansa ODTÜ'de devam ettik ama ben bir miktar ihanetle karşı bölüme geçtim. Elektrik elektroniğe. Ulaş Hocam o sırada lisansını ve yüksek lisansını ve doktorasını Melik Hoca ile birlikte yüksek teknoloji, geleneksel olmayan üretim teknoloji üzerine devam etti. O zamanlar daha oldukça yeni olan eklemeli imalat alanına yöneldim.
Doktora da hocam aslında çok fazla eklemeli ben çalışmadım.
Aynen
Daha
öyle.
sonra da çalışmaya başladım.
Genel olarak ama üretim
Evet.
teknoloji.
Evet.
Ondan sonra doktorasını bitirdikten sonra Perth Üniversitesi'nde yok davetli öğretim üyesi, artık yardımcı doçentti. Şimdi doktor
Hı
öğretim
hı.
üyesi olarak hayatına devam etti. O sırada da çok daha farklı bir şekilde hani Türkiye'ye dönmeyi planlıyoruz. İkimizin de Amerika'da çocuğu olmuş. Birlikte görüşüyorduk ki Amerika'da çocuk doğurmak, büyütmek çok da şeydir. Aslında aynı zamanda ODTÜ'de başlayacaktık ama bazı şanssızlıklardan dolayı ben bir sene daha sonra başladım. Ulaş Hocam burada mükemmel işler yapıyor. Gerçekten çok farklı alanlarda çok güzel işler yapıyor. Kendi araştırmasının yanında bize aslında mentorluk yapıyor. Yani 3 boyutlu yazıcı üretim konusunda sürekli ona gidiyoruz ve sağ olsun bir kere bile artık yıktınız demedi. Yani ROMER'in üretim danışmanı da diyebilirim. Onun konuşması dinlemekten hem arkadaşı hem de birlikte çalıştığı araştırmacı olarak da ben mutluluk duyuyorum.
Teşekkürler Mert hocam. Peki abi. Bu arada hocam ben İngilizce hazırlamıştım ama Türkçe mi devam nasıl yapalım? Tamam, okey. Sonra gerekirse zaten şey yaparız. Çok özel şeylerinizi de Türkçe'de konuşabiliriz yani. Okay, welcome to the seminar and I will now quickly start and thank you for the introduction, Mert hocam. And today I will briefly discuss what are we expecting from additive manufacturing in near future and maybe in 20 years, in 50 years, what kind of methods we will see and what kind of materials we will see and what type of applications we will employ with additive manufacturing. I will show you some examples and I put lots of videos inside. So I hope it will not be boring and I will give you lots of information. And by the way, I'm from mechanical engineering department and recently for about 3 months, I've been assigned as the head of welding technology non-destructive testing center. I'm trying to actually include additive manufacturing into the center. We will try to use non-destructive methods and welding for additive manufacturing and try to come up with some research topics and have some more outputs from these topics. So since Mert has mentioned my CV summary, but I would like to mention about Turkish Additive Manufacturing Association since it's related with the topic of today. I'm vice chairperson of Turkish Additive Manufacturing Association, and we have formally been established last year. And we are organizing an annual conference in Turkey. It's quite actually a good conference, and about maybe 30 participants presentations will be from abroad, and there will be 60 more presentations from Turkish people. So if you're interested, you're always welcome. You may just Google it and find some extra information about this conference. So what I'm going to talk about today, I will briefly talk about the history of additive manufacturing, and to make sure that everyone knows additive manufacturing methods, I will describe 7 fundamental additive manufacturing methods briefly, and then I will talk about what kind of materials have been developed recently, what kind of approaches have been invented, like liquid metal deposition, viscous lithography manufacturing. I will talk about these, and I will always show some videos to make sure that you understand the process in detail. And then I will show you some various interesting applications of additive manufacturing, since additive manufacturing is not just a kind of, let's say, a manufacturing method, but you need to also change how you're designing the products. If you cannot design the parts properly, then you will not be able to taking advantages of additive manufacturing. So I will show you some interesting examples and then talk about what are we expecting in near future, and again show you some pictures and videos, and lastly I will conclude my present. And this is the video recently I have taken in November. So you see they are using again robots, and robotic additive manufacturing is another field. Maybe that is highly related to obviously ROMER, this sensor. And you can see we have a little extruder here, and robot is just responsible for the rest of the motion. And the extruder, as you see, is not moving. It's just stationary. And at the back side, we have a feeder. It's just feeding material, but the rest is done with this robot. So how things actually started? This is a very old patent, as you see. It was filed around 1925 by, as far as I remember, it was Ralph Baker. And he thought that he can make use of actually welding process to manufacture some products. This was his idea. So you see the title is Method of Making Decorative Articles. So this was a very old idea, but recently we are using robots again to manufacture actually some complicated products with again welding. So it was actually the start of maybe some additive manufacturing methods. And formally, actually, in textbooks, we just described this one. This is one of the patents applied in around 1980s, and it was based on resin material, a liquid-based material. I will again talk about this. And they have, as you see, some schematics about it. And then later, they have established a company, and this is the company's 3D Systems, and it's now one of the biggest companies of additive manufacturing. And they are still using this technology, but they also have some other technologies now in their portfolio. But recently, maybe a month ago, I realized that actually things actually goes back to more about maybe 4,000 years ago, 5,000 years ago. People were doing some kind of additive manufacturing, but obviously they didn't know that it is additive manufacturing. So what they were doing is that in order to manufacture such jars, cup-like shapes, they were preparing such coils and putting them on top of each other. So they are kind of adding material on top of each other. And then later, by doing some rotation, they do some forming on it and try to manufacture the final jar. And then recently, not much recently, but about 10 years ago, Murat Türk'teki actually found some articles around Eskişehir in Küllüova, and they have done some X-ray analysis, and you can see that, you can see the layers actually. The same coils these guys were doing about 5,000 years ago. You can see the coils, the layers, and obviously they're not perfect, but they don't need to be perfect since they were used for actually storing some articles. So as I mentioned briefly, although things start in 19th, 20th century, but in reality, it was started about 5,000 years ago. So now we have if you standardize these methods, there are several additive manufacturing methods, but now ISO and ASTM have agreed that there are 7 basic types. So if you come up with an novel additive manufacturing technology, probably it will fit into one of these. Whether it will be an extrusion method, whether you are using a resin material and then polymerizing them, whether you are jetting the main material. I will talk about these, by the way. I'll show you some pictures, but in some of them, we are making use of powders, and then in some, we are jetting binders instead of actually jetting the main material. Then in the last two, we make use of mostly laser or arc sources, energy sources, to actually melt down materials and then try to manufacture complicated shapes. And lastly, this is, we don't have actually much technology underneath this one, sheet lamination. It's not that mature yet, but probably we will have more companies, more technology, more systems in the upcoming years. So I will, as I said, briefly talk about all these technologies so that everyone knows what I'm talking about. This is the first one, and maybe most of you have experienced this material extrusion method. We make use of filaments, and then we have a feeder. This is not shown here, but filaments are fed into this extruder, and since temperature is high around here at the tip of the nozzle, we extrude material, and since this actually head is moving on the XY axis, and we can deposit material along this paths and try to come up with 2D layers. And if you repeat these layers many times, then you will obtain such complicated shapes. And another thing is that if you have complicated shapes and you may need to use some support structures, I have, for instance, some examples here. There's a little bunny, and as you see, it has kind of ears which is hanging. So we need to support the ears underneath. Otherwise, while printing, since this is done by layer, they will fall on ground. And in order to keep them in place, we make use of support structures as shown here. And this is, by the way, the most common type of additive manufacturing methods. It's the cheapest one, and we can make use of several materials. And another thing is that we can employ this method for various approaches. We can use concrete even to print some simple structures or buildings, or we can make use of some cells and try to come up with bioprinters, or even we can use some chocolates. Since if you just increase the temperature of chocolate, then it will be in semi-solid state, and you can easily push it through the nozzle and manufacture some complicated chocolates. Or even pizza, if you want to make pizza, you can prepare your ingredients and then maybe have several of these heads, and you can easily extrude your materials, ingredients, and try to come up with some new food. So that's why actually, due to the simplicity of this approach, many people are using material extrusion for various purposes. And the second one, this was actually the first type of additive manufacturing invented. It is stereolithography, but we have some variations of this one. It uses photopolymers, a liquid type of material actually, and sometimes we call it as resins. What we do here, actually, if you want to turn this state of photopolymers from liquid to solid, then you need to actually polymerize them. And to polymerize them, we need to use light sources. And here we are using laser, but it doesn't need to be a laser. You can even use some UV light or different light sources. The thing is that the energy level at this point should be higher than the critical energy level. And then actually photopolymerization will start, and our resin material will now be solid. And I have another example here. This is, by the way, the same model. And you see that again, we have used lots of support structures, since the product is actually manufactured inside a liquid tank, but liquid itself obviously will not be able to support these overhanging regions. So we need to have solid support structures. And the main advantage or difference with respect to previous technology is that it is highly accurate. If you have time, maybe after the seminar, you can touch these and you can sense how actually good surface we have with the SLA technology. But the thing is that we need to have high amount of resin in the tank. So you see this is the fifth number is the tank itself. So we need to put too much material, and we need to then later our laser will follow a defined path. And you see that we are making use of mirrors, galvanometers, to make sure that it is much faster. If you just put a laser underneath and if you move laser, then it will be quite slower. So that's why people usually make use of such galvanometers and try to scan the layer as in low amount of time possible. And we have other variations like clip, DLP. I'm not going to discuss these, but in these, the light source is different. Instead of actually lasers, they make use of projectors. So they do actually, they scan or they do the polymerization of a layer at a time. So it's much faster. In few seconds, they reflect the image, and then the whole layer is actually cured. The third method is material jetting, and this is somehow it has some similarity with the previous one. It is using again photopolymers, as you see, in resins. What is different? Instead of using a tank, this time they are jetting the photopolymer material from these heads, and once they actually deposit them, you see that the third item here is actually a UV light. So with the help of the UV light, polymerization starts and your jetted drops actually become solid and you can manufacture parts. Again, the rest is the same. Our head need to move actually on X and Y axis. And after one layer is completed, we need to lower down our table. And again, it has high quality, like in the case of SLA. And then another thing is actually this is quite expensive, maybe due to the patents they have. But since they're not using a kind of a tank, they don't need to start with high amount of material. So we can say that it's actually more sustainable. Then comes the other additive manufacturing methods. This is these days much popular, especially for metals. So you see that I have put two images. The reason is that the technology is almost the same, but there are little differences for polymers and for metals. The structure is almost the same, but you can see that the main difference is the support structures. Although you are printing the same design, same model, in polymers actually, you don't need to support underneath. If you even have overhanging regions, that's not a problem. But for metals, there are several regions we need to have support structures. First of all, it gets heavier. Another reason, the temperatures are very high. So with the help of these extra structures, what we do, we actually transfer heat and try to decrease the temperature difference between the layers so that the quality of the part is improved. And in both of them, actually, we can later, after the parts are produced, we can recycle the powders. But the thing is that the surface quality is usually not good. And another important issue with polymers, actually, you can manufacture assemblies as they are. You don't need to manufacture them one by one. You can put whole complete assembly into your actually printer, into the software of your printer, and then the whole assembly will be printed as it is. After they are produced, you don't need to do the assembly thing. Then we have binder jetting. So it is just actually a combination of materials jetting and powder bed fusion. So you see the schematic is almost the same. If I go back, we have a powder bed. Again, in binder jetting, we have powder bed, but the difference is that instead of a laser, we have a jetting head, and this jetting head is responsible for depositing these binders so that the powders will be joined together. But the problem is that once you take this product out of the printer, it is not strong. We call it as green part. Maybe you can even break it with your hands. So what we do, we need to perform different type of secondary operations. For metals, we prefer to do infiltration so that the gaps are filled with different metals and the strength is improved. But for ceramics or for other type of things, actually, that may not be a problem. Just sintering may be fine. And we can make use of another thing about this process, that we are not limited with materials. We can make use of plastics, metals, ceramics. For instance, in metallurgical department, Eda Hoca is actually working on metals by using binder jetting technology. And last week, I visited a company in Izmir, and they were using this technology to manufacture ceramics. They were depositing ceramic powders, and then with proper binders, they were joining the powders together and having some ceramic parts printed. Another technology is direct energy deposition, and this is actually especially good for metals, and we obtain quite stronger products. And as the name implies, we have an energy source, and we need to direct that energy source to the tip of our nozzle. And at the same time, we are depositing material, and with the help of the energy source, we are melting that mostly metal. It might be in the powder form or in the wire form. If it's wire, we may make use of simple lasers, or sometimes we make use of arcs, like we use in actually welding process. And for the powders, we mostly make use of actually lasers. And the thing is that usually we need to have a protective environment around this deposition so that there will be no oxidation and no other issues about melting. And since if you do not have a protective environment around your melting pool, then probably you will have several defects, porosities in the final product. And this method further can be used for repairing purposes. So assume that you have a large piece, very large product, and you have a robot. Maybe at the tip of the robot, you have a laser and a powder depositing unit. So you may bring your robot beside the product and then try to fill some gaps, some cracks, so that the cost of your overall manufacturing of a new product will be reduced. Or you can do this process for coating operations. But again, it's quite expensive. We make use of some lasers. Materials are specialized. Another thing, this has quite high surface roughness since controlling of the melt pool is not easy. Another thing, we are depositing material using powder, so the quality is not good. But the advantage is that the product you're obtaining usually has high density. Since you are depositing more material, and sometimes you make use of high speeds for that, so that increases the density of the products. And the last type of method is sheet lamination. As I said, this is the least mature type of additive manufacturing. We are still working on that, and maybe people didn't find any application areas. We can make use of actually sheets of papers, metals, and composites. So what we do, we put them on top of each other, and then with the help of a knife, as you see one of the patent here, it doesn't have to be knife, but it needs to be a kind of a cutting tool or a laser. You will go over the outline of the layers and then try to print the products. And another issue in this process is that since we are putting layers on top of each other, we need to have a proper connection between the layers, and that can be obtained by making use of some adhesives, or if you are making use of metals, then you may go with actually ultrasonic welding. It's totally different topic, but this is maybe one of the interesting research areas these days. So now I hope that you understand the types of additive manufacturing technologies. There are 7 of them. And now I will talk about what kind of contributions have been done recently in terms of materials and in terms of technologies. So if you briefly talk about materials, if you consider conventional manufacturing operations, we know that we don't have any limitation. We can make use of, we can machine wood, we can machine plastics, metal, so there is no limitation. But in additive manufacturing, we have some low numbers of materials available for plastics, for metals, so we are limited. And that's why we cannot easily manufacture what do we have in mind, or we cannot have counterparts of each artifact. And that's why these days material researchers, material scientists are always trying to come up with different materials for additive manufacturing. And these materials might be in the form of powders, filaments, and resin. And so you have seen the technologies. Some of them were using powders, some were using filaments, wires, and some were using resin materials. So if you come up with some novel materials like this in one of the forms, then you can maybe use them on the available technologies. And another interesting thing is that actually most of the new materials are coming with resin materials. Since probably its research is much comfortable, we can put new additives inside this resin material and come up with different materials. So if you come up with materials, new materials, then probably you can come up with novel applications. Since in most of the projects, actually, we are limited with the material. But if someone invents a new material, then we may think of using that material in different areas and come up with some useful applications. Now I will show you some examples of them, of recent contributions. And for a few years, maybe about 5 years, we are these days using chopped carbon fibers, actually. We put little fibers inside plastic filaments, And here you see an example picture here. About 50% of the volume actually is filled with chopped carbon fibers. And the thing here is that if you increase this percentage, then probably the printers will not be able to extrude that filament. And that's why they are limited around 15%. Another thing we are using in terms of fibers these days is the continuous fibers. And ROMER actually has recently purchased a kind of a printer which uses continuous fibers. So that is much useful. We can even obtain some products having maybe strength values close to at least some simple metals. And another interesting topic is that we are these days putting some metals into filaments. So filaments are obviously made of plastics, but in order to increase their strength, what we do, this is a cross section of a filament. You can see that metal powders are embedded inside this filament. And the thing is that even though it has metal inside, but we can use the same machine, the same printer again, and print some metal products. But the thing is that your printed metal part will have some plastics. So as you see, about 70% of the part is containing metal powders, but 30% is made of plastics. So what we do, after you make use of these filaments, you need to do some debinding operation so that you remove plastics away, and then you do sintering operation. You kind of melt the product so that these powders are actually fused together and you have a proper connection between the powders. So it is doable, but not easy. We have also some improvements, recent improvements in terms of actually wires, and we can try to use actually different materials at the same time. Or we can have some cord wires, or even we can put metals inside, but plastics outside. So these are some combinations of approaches. But the thing is that obviously your extruder, your system should be able to extrude these null materials. And we don't have any commercial applications of this approach. Probably they haven't optimized maybe some of the settings, or they haven't come up with a proper 3D printer which can handle these difficult materials. And in terms of resin, there are many companies working on different type of materials. And as I said at the beginning, it's much easier to come up with null materials here, since into resin, you may put some ceramic powders, or you may change the chemistry and try to make it flexible, or make it tough, or make it flame retardant. So there are different type of resins we can easily obtain. And in terms of powders, polymer powders, I have a nice example here. Recently, actually, several companies gathered together and they worked on a project. And the idea was to manufacture a basketball without using any air inside. So that's why they call it as airless basketball. And you can see how they have manufactured it. It has the same dimensions, same weight with the conventional basketball, and they use flexible material. I have, for instance, a flexible material here. You see, it acts like a ball. And they have done a great job, actually, but printing is not enough. Since you need to clean all the powders remaining inside, and then later you need to apply some surface treatment so that you feel like a basketball. But if you feel it, this is made of plastics. I don't feel that it is in plastic. It's a basketball. But they have done, as I said, several operations, several secondary operations, and try to come up with the real feeling of a basketball. And later, they have done simply some painting. And a few months ago, actually, they start to sell this one. Actually, Wilson start to sell this one. And can you guess the price of this basketball made of 3D printers?
2,500.
Yes, probably you have seen that. But that was really like a basketball. I actually had a chance to play this one in November. I also did some shooting, but I haven't recorded that. So in my first try, it was short, but later when I accustomed to that, it was actually a basket. So yes, as I said, in my first try, it comes short actually, but in my second try, I somehow did it. So probably the basketball professional ones will not play with this one, since if they get accustomed to this one, then in the game they will play poorly. So maybe in future, and I think they have used this one in one of the dunk championships in NBA. Since while dunking you don't need to do anything, just if you grab it, that's enough. But for shooting, yes, the dynamics is completely different. So probably they need to work a lot and maybe come up with some different ideas. And the issue about this ball is that after actually Wilson launched this ball, then everyone started to print their basketball themselves. In different companies, at home, people started to come up with some different balls, and they also focused on American football ball, but they haven't tried football since it's not probably durable. But they also tried, as far as I remember, baseball and American football. I have also some other things about the materials. So we were talking about powders. So the previous slide was about polymer powders, and for the metal powders, these days the trend is to make use of different metal powders at the same time. And in order to do that, your machine should also be able to deposit two different powders at the same time. Since if you remember the technology for this powder spreading, powder bed fusion, do you remember the sketch? So we have a kind of a spreader, but if you have two different powders, then how it's possible? Since we have a larger spreading head, it's moving and spreading powder, but if you want to spread another metal, that is not possible. So what they do, they come up with some different technologies. They make use of vacuum, they make use of electrostatic forces, and try to deposit, as you see, this time steel and copper at the same time. But here the question is, do we need this? Actually, do we need to have two materials at the same time inside a part? So they have come up with a novel solution, but these days they are trying to find some applications so that they can sell their product. But right now, the only advantage is that if you use copper, it's in some critical sections, then you may dissipate heat easily there, but use steel for strength actually. So if you find such application, then that might be useful. But for other issues, we can print by using a single metal powder. And another thing, actually, this is how we learned up to this day. Since in metals, we are always printing something or manufacturing, machining something out of a single material. Since we are not accustomed to that, we cannot come up with ideas where we can make use of several metals together. And there are several companies actually working on this technology using several types of metals at the same time. Another recent approach actually for metal powders is regarding the binder jetting technology. If you remember, in the binder jetting, again, we were spreading powders, but this time we were depositing, jetting some binding agents. So what they do, they come up with some special powders having some chemicals, additives around, so that they claim that you can obtain parts with lower porosity. Since if you remember, I said that binder jetting is quite tedious. You need to perform several operations after you are done with printing. And then they claim that if you make use of their powders, then you can simplify actually secondary operation, maybe less number of operations or less difficult operations you need. And we also have some improvements in sheet materials. And what are we doing? Actually, we are trying to put, again, different type of materials on top of each other. And then later, you may do maybe some machining and again, open some nice channels for maybe cooling for other heating applications. And not just metals, but we can even have some carbon fibers, glass fibers in between, so that, again, we can increase the strength of the products. So this is actually all I can say for the materials, but I will talk about maybe it will be more interesting, I guess, the approaches, what kind of novel approaches we are developing. And in order to come up with a novel additive manufacturing technology, a new method, you need to also have some improvements in different technologies. Like for instance, improvements in projectors, improvements in laser technology, improvements in computer technology. After all these are developed, after you have such matureness in these technologies, then you may think of developing new additive manufacturing approaches. But besides, we also have some ad hoc solutions, so some little solutions for the existing ones, so that their performance will be increased. And I will show you some examples of two categories. And I can say that most of the novel technologies are based on resin material. They are not based on powders or filaments, but they are mostly based on resin material. Since it's much easier to process, you don't need to apply high energy. It's in liquid state. So that's why actually novel metals are usually come up over resin material. Let's start from this one. And by the way, this is not a new technology, but it's an ad hoc type of solution for the metal 3D printing systems. I'm not sure whether you have realized what is going on here, but the thing is that in the conventional approach, what we do is spread powder. Once spreading is done, then laser actually, like on me, actually, it goes over the table and it melts the powders. But what they do here doing is that while spreading powders, laser is working at the same time. You can see that now in a moment. I will show you that. So you see laser is working and also it's working at the back side. But conventionally right now, almost all metal type of 3D printers wait for actually spreading operation. After spreading is finished, they start actually melting the powders. But they are doing something different so that they gain actually 9 seconds per layer. So if you are producing a very long product, this makes a lot. And if you think of additive manufacturing being used in critical applications in the upcoming years, then that will be quite important. And this is another ad hoc type of solution, but this is quite straightforward. What they do is that instead of using a single laser to decrease fabrication time, they use, as you see, in maximum 26 lasers at the same time. So that manufacturing is decreased a lot, time is decreased a lot. But the difficulty is that you need to divide your actual slice into proper regions, and you shouldn't have any collisions, and you shouldn't have too much difference between the regions of two lasers. You need to have smooth transitions between the regions. But obviously, that saves lots of time. And now this is a completely novel technology. Probably you have many of these, but right now this method is only working for aluminum. Since aluminum has low melting point temperature, and that's why they can actually extrude it. But for steel, for other materials, it's not that easy. And the rest is actually not complicated. It's like actually material extrusion. We have the nozzle, they are increasing the temperature, they are melting material, melting aluminum, and then depositing it. And since it's solidified quickly, that's why even for surface having a 75-degree angle, they can manufacture it without using any support structures. Another thing, since temperature difference is not much, again, we have less residual stresses so that the quality is maintained and the dimensions are quite good. And this is another novel technology, and you can see that that is based on resins. But the difference is that they are using highly viscous material. It's quite special material, and you can see how actually difficult for it to move, but still it's a resin material. And here they actually combine several technologies to come up with a novel technology. You can see that they are using projector for curing, and these structures are like actually extruding process. And another thing, they can use two different materials, one side, one tank for support structure, one tank for main material. And now you see that in a moment, this guy actually will take some material and put it onto the film. So it becomes like a sheet lamination. But I cannot say that this is purely sheet lamination. It uses some steps of sheet lamination and some steps of stereolithography. And they claim that actually, with the help of some extra chemicals inside the resin, they manufacture some stronger products. Another thing, since they're not using a tank and they recycle unused portions of this film, so this is quite sustainable. But the thing is that it's not yet commercialized. Maybe intentionally they're not commercializing it. They're trying to get some manufacturing orders from the customers and manufacturing the parts themselves. But I think maybe in a few years they will start selling their machines. And in summary, I can say that this is good for mass production, especially for larger plastics. And you can see their viscosity and two different materials, but they are not mixing. So let me continue with another type of actually novel technology. This is called rapid liquid printing. It's actually it was invented at MIT about maybe 7 years ago, but they couldn't commercialize it yet, since they couldn't find novel or fancy applications. So you see that we have a bed of gel. So it's like actually powder bed fusion methods. But what is on here is not shown, but they have like an injector. They put the injector inside and then it goes over the pad and deposits plastics. And it doesn't need to have any support structure. But the thing is that we cannot easily use the outputs of this process. Instead of this process, I can use cheaper material extrusion or stereolithography. Why should I use this one? So that's why actually they couldn't commercialize the system yet, but they are trying to find some biomedical applications, maybe flexible, maybe in robotics, soft robotics, they can print some simpler shapes which can extend themselves under pressure. So after that point, maybe they will commercialize it. Another novel approach, and this is quite different than the previous ones, but still, this one is also using resin material. And the idea here is that for instance, in material extrusion, what we do, we extrude some material and go over a specific path. And this is point-based manufacturing. And sometimes, if you think about material jetting, what we have on the head, we have several nozzles. And if you move your nozzle like this, then you will be doing one-dimensional kind of actual printing. And if you make use of projectors, if you reflect your image and cure the whole layer at a time, then that will be 2D manufacturing, 2D type of curing. But here, they are trying to actually cure the products in a different way, actually by using not completely 3D, but 2D time, maybe plus and linear movements. But my idea is actually, my dream is to actually manufacture a product in some seconds by using several projectors. So you will have a kind of an resin inside this one, let's say, and then you will reflect light from both sides, and in few seconds, your material inside resin will be cured. It's like actually holography. That's why actually they call it as exolography. I think in near future you will see such an example, since as far as I know, there are several universities working on that. They should actually come up with a proper resin material. Since if you are reflecting or light from different sides, then your material should be able to cure itself under these conditions. And the advantage is that, as you see here, it takes about 65 seconds. But in my idea, if you have the proper material, if you have the proper equipment, hardware, then maybe in few seconds, you will be able to manufacture the complete product. Another technology, recent technologies actually evolved. So even though they have put some video on their website, it's not clear yet how their method is working. And another thing is that they are again not selling the machine. They are getting orders from the customers and manufacturing the products for the customers. You can see, for instance, an example here. It is made of ABS material. They can only use few materials right now. They use again some light technology, some resin technology inside, but even though they are trying to describe these methods in this video, it is not clear. They have some patent issues, and that's why they're not giving much information. They are not selling their machine. And obviously they have closed loop control systems at every part, so that you see they obtain high quality products at high numbers. So that technology is quite useful for mass production. Another novel technology is the composite-based additive manufacturing. This is actually, they have got some investments from different companies, so probably we will be seeing some of these in near future a lot. And they start with some composite sheets, and then they deposit some extra chemicals on the sheets, and then cut these sheets and put them on top of each other to obtain complicated composite materials. Since if you are into some composite world, you know that they are mostly simple shapes. They are sheet-like materials or some simpler geometries. But here you can see that they will come up with a complicated product. Another thing, they can put not only carbon fiber, but they can also put some glass fiber inside. So they are using some water, but depositing water selectively, not to each point, and then depositing some polymers on that so that it will stick to these points, and they will obtain the layers. And then they will do some cutting operation. They will cut the layers and put the layers on top of each other in a moment. And this is cutting operation. And they will further cut down into single layers and do some pressing. So now let me show you some nice applications of these additive manufacturing technologies. First of all, these days we are trying to, as I said, always come up with some fields where we can use additive manufacturing. One of them is to manufacture such cutting tools in machining, and conventionally they are made by powder metallurgy, but instead we can make use of additive manufacturing. Or these days we can make use of customized musical instruments. You can change the size, you can change the pattern. So we have such freedoms, and probably we'll see more of these in near future. Another one is actually we are using additive manufacturing these days a lot for heat exchangers. You may even have such complicated channels, little channels inside. So you see that from one side we will have hot fluid, from the other side we will have cold fluid. And with the help of additive manufacturing, we can easily increase surface area. And surface area, as you know, is highly important in heat exchangers. You want to try to increase it as much as possible, and that is possible with additive manufacturing. Another applications we will see more in the upcoming year is the large area additive manufacturing. So these days we are mostly printing smaller items, but in near future we will have larger ones, and for maybe preparing the tools for composite manufacturing, or maybe manufacture some buildings or manufacture chassis of some larger systems, even vehicles maybe. We will see more of these. Another field we will see additive manufacturing a lot is the aerospace. And for instance, Relativity Space Company has recently manufactured the body of the rocket out of just additive manufacturing. They used wire arc additive manufacturing, and they also have small components, but the whole body, this body which is quite larger, it has been also manufactured with wire arc additive manufacturing. And what are we expecting from additive manufacturing? First of all, we will start using, right now we are using robots, but we will use more robots in additive manufacturing so that we can have complicated shapes and we can produce larger products. And we are trying to make additive manufacturing as sustainable as possible. So we will try to find some ways to use less material, less energy, or we will again see lots of additive manufacturing, concrete building actually. By extruding concrete material, we can manufacture some buildings. For instance, recently in Saudi Arabia, they have manufactured a mosque. They have constructed a mosque by using concrete 3D printing. And we will have high performance in metal manufacturing, metal additive manufacturing, and we will probably see use of copper in most of the applications, since it was quite difficult in the earlier years, but now we have some control on the copper powders, and we can manufacture more parts made of copper. Another thing we will see is the mass customization. So the products we are purchasing will always be customized according to our requirements. So first I will purchase like maybe a pointer which will exactly fit into my hand. So this will be possible in the upcoming years. Another thing we are expecting is the mass production. So these days, most people are actually criticizing additive manufacturing as being slow, quite slower. So that's why people are always looking for some ways to increase their speed. So we will probably see such systems having multiple heads, multiple lasers. Maybe we will be printing many parts on top of each other so that the overall manufacturing time is reduced. And again, for mass production, we can make use of robots. And lastly, we will see more of these 3D printing farms. So these days, even some companies have some rooms of several 3D printers. They are connected to their automation system, but we will see more of them in upcoming years. And another thing we are expecting actually, since people are not using additive manufacturing completely for their manufacturing, but they can use additive manufacturing on their conventional lines so that their overall efficiency will be improved with the help of using additive manufacturing beside conventional systems. And another expectation is that we will have high quality printers in near future, and their prices will not be that much, so that people can purchase high quality printers for their home and try to manufacture at home. And furthermore, we will see some new approaches, new applications in the education fields, in business models, and also software, especially design analysis software you have in the upcoming future. So let's summarize. So you have seen that there are many expectations from additive manufacturing. I hope all of them will be satisfied, will be covered, and we will see more applications of different materials, different approaches. And another thing we will see is hybrid manufacturing. So we cannot completely replace conventional manufacturing operations with additive manufacturing. So instead, what we will do, we will combine them together and try to take advantage of conventional systems and additive manufacturing methods. And another thing, probably, if we are at some time, if we are going to live on the moon or on Mars, then probably you'll have some systems manufacturing some buildings for us with the principles of additive manufacturing. And another thing, these days we will have, as I said, some limitations in terms of materials, but we will probably be inventing some more materials so that some parts which cannot be manufactured on the conventional machines will be manufactured on the additive manufacturing systems. Another last thing I can say is that with additive manufacturing, as you know, we don't have much limitations in terms of design, so we will have more applications of these design freedom with the help of materials and with the help of applications. Well, this is all I can say for now, but if you have questions, we can discuss some topics.